Hello everyone, good afternoon. My name is Brendan Kellogg. Thank you for coming to the talk today about carbon budget of Centropages hamatus in the warm Gulf of Maine. My two co-authors are Dr. David Fields and Maureen Musto. They're both affiliated with Bigelow Laboratory for Ocean Sciences, which I was at for a research experience for undergraduates last year that was funded by the National Science Foundation. Thank you, NSF. So last talk we were in California, so let me take you across the United States to the East Coast, specifically the Gulf of Maine. It's a beautiful stretch of water that goes from the Bay of Fundy to Cape Cod. It's home to numerous ecological and commercially important species such as cod, lobsters, charismatic megafauna like the right whale, and copepods, which are the step between primary producers and higher trophic levels. But there's a bit of a problem. The Gulf of Maine is warming faster than one of the fastest warming bodies of water on the planet, as you can see from the graph on the top, which is the sea surface temperature anomalies over 40 years from 1982 to 2021. The line in blue is just the averages over those 40 years, and the dashed line in green is the global sea surface temperature anomaly. So as you can see, the Gulf is warming faster than the rest of the world. The bottom graph is just a heat map of just 2021 of the Gulf of Maine, and it's all red, so there's no cooling, it's all hot, which is very unfortunate. And why is the Gulf warming faster than other bodies of water? Well, there are a few reasons. One, the Gulf is relatively shallow, reaching 370 meters at its steepest point. It's also a relatively enclosed system. And the Scotian current, which brings cold water into the Gulf, is slowing down and being overtaken by the Gulf Stream, which brings warm water into the Gulf. And as the Gulf warms, there's a bit of a regime change in the copepod species that appear, with Calanus fin marchkis moving north to colder water, and smaller copepods like Centropages hamatus are becoming more abundant as the Gulf warms. And this is Centropages hamatus. It's a, oops, shoot, don't look at that, that's a spoiler. There we go. This is Centropages hamatus. It's a calanoid copepod that ranges from 0.9 to 1.35 millimeters in length. It has a fairly unique morphology with a head and shoulders type morphology and two spikes on its posterior chromosome that are sexually dimorphic. And I really wanted to look at how the warming Gulf was affecting this under-researched copepod that's becoming more abundant. And I did that by looking at its energy budget, specifically the carbon that's taking in and the carbon that's being let out through respiration. So when an animal eats, it just needs that energy just to exist in the world. But any extra energy is used for its scope of growth, the energy that it has for growth and reproduction. But since I only used adult Centropages in never longer than a period of 24 hours, and I didn't look at fecal pellets, we're really just looking at the carbon that's being ingested and the carbon that's being respirated out. And I did that. Well, first I needed some copepods, so I did a lot of net hauls, vertical net hauls with a 0.75 meter diameter, 200 micron mesh plankton net in the Damariscotta River that was very close to Bigelow Labs. I just caught copepods as I needed. I then sorted Centropages out of those copepods and then acclimated them to my testing temperatures at 8, 12, 16, and 21 degrees. And please, you should definitely ask me how many Centropages I caught, because it was a plankton. Alright, so to start, I needed to get to carbon, I need to go through oxygen. So I used 4 Unisense oxygen probes to measure Centropages oxygen consumption. I used 5 milliliter respiration chambers, and I immersed with 10 copepods in them each, and I immersed them in a water bath at one of my testing temperatures. On the graph at the bottom, you can see raw data from one of those tests, with the lines on top being my control and the line in green being my test chamber, and that's the micromoles of oxygen present in that respiration chamber in that water over a period of 2 hours. And as you can see, there's a pretty stark difference between the two. For grazing, I filled a 260 milliliter bottle up with a 2 times 10 to the 4th per milliliter concentration of Thalassocyrus flagii, and put 20 copepods in them, and then I strapped them to a plankton wheel that goes half a rotation a minute for a period of 24 hours. I then use a MOXIE cell counter to count the amount of cells after that period of time to see how many cells they ate. So this is the graph from the oxygen consumption experiments. As you can see, the oxygen they're consuming increases as temperature increases. And I'm very proud of this because I have an R-squared of 0.96, which is really cool. What I found interesting is that the oxygen consumed basically doubles from 8 degrees to 21 degrees. But we're not really interested in oxygen, we're interested in carbon. But to get, and you would assume theoretically that 1 mole of oxygen would equal 1 mole of CO2, but that's not really how it works in the real world. So we assume a respiratory quotient of 0.82. This is the respiratory quotient is the volume of carbon released over the volume of oxygen absorbed during respiration. So now that we have the micromoles of carbon released, we can then use its molecular weight to get the micrograms of carbon released per copepod per hour, which also increases as temperature increases. So we've been talking a lot about respiration, the carbon that's exiting the system. So now we're going to get into the ingestion, the carbon that they're eating. On the bottom left, you can see the cells in per copepod per day. You will notice that I don't have a temperature point at 8 degrees. That's because both of my experiments at 8 degrees failed for some reason. But we still have some very nice data here. There's a pretty dramatic increase from 12 to 16 degrees and a slight increase from 16 to 26. But again, we're really not interested in the cells. We do not care about it. We're interested in the carbon from those cells. So using the Mendenhall-Losar formula, we can get the amount of micrograms of carbon per cell, so we can see how much they're eating. You can see that on the secondary axis here, the micrograms of carbon per day. And I also decided to run some Q10s because of that pretty dramatic increase from 12 to 16. What a Q10 is, it's a rate of change normalized to 10 degrees. So the Q10 from 12 to 16 is 2.39, and the Q10 from 16 to 21 is 1.52. So now we have both the carbon respirated out and the carbon coming into the system through ingestion, so we can look at the amount of excess carbon these animals have, which you can see here. And you'll notice that everything's above 0. They always have excess carbon for growth and reproduction, which is very nice to see, even at a high temperature of 21. But what I find interesting is that at 16 degrees, it seems to have, it's the highest, so it seems to suggest that there's an optimal temperature from these, at least at these points, temperature points that I tested using just carbon ingested and carbon respirated out. For future work, I'd like to look at the fecal pellets as another way of carbon lost, but I don't think that it would have a dramatic increase. I'm pretty sure there'd still be excess carbon in their systems. But I'd also like to repeat these experiments with Centropages typicus, which is a slightly larger Centropages that's found more in open water. And then I'd like to look at the caloric value difference between Centropages and Calamus monarchicus to see how many Centropages it would take to equal the caloric value of Calamus, since Centropages are becoming more abundant. And I'm super under time, so. I'd like to thank Dr. David Fields, who's in the audience somewhere. Omar Nimaso, my fellow interns, Ali Umet, who I also believe is in the audience. Hi, Ali, and Ruben Magani. I'd like to thank Bigelow Laboratories, and I'd like to thank BNSF again. And a huge thank you to the ASLO Multicultural Program, without which I would not be presenting today, as they provided the airfare, the hotel, the food, the space to present this research. Thank you very much, ASLO and and thank you all for listening. There are a lot of time for questions.
Thank you, Brendan, with such a dynamic voice. Should we go to like announcing or like audiobooks one day? He did say we do have time for like 4 to 5 questions. Shoot them away.
As I said, that was a great presentation.
Thank you.
Love the voice style as well. Just a quick question. I thought when you were showing the amount of carbon that was produced at a certain temperature at 16 degrees, do you have any idea why at 16 over 21 that's the optimum carbon inside the copepod body?
I have no idea why, and I am really bummed out I didn't get the 8 degree temperature point for that. And since it is like optimum at 16, I'd like to like even go further beyond and see at like 23 or 24 if it is even lower.
If it decreases?
Yeah, if it decreases more.
great presentation, Brandon. I had a question on oxygen consumed increase. As heat increases, do you ever think that you're going to do like further research on that region?
About if the higher temperature, the more oxygen you're consuming.
Yeah.
Yeah, I think if I do more, like the previous question, if I look at higher temperatures, like I'll definitely see if oxygen is being consumed even higher at higher temperatures. That's another thing I could do.
And
Great talk.
Thank you.
So I'm curious, I do ocean acidification work, and a lot of times we couple the change in pH with also changing the temperature. So how do you believe that changing the pH will affect, I guess, the carbon dioxide that they expel and, as a respirator?
I have no idea, but that's a really good question, and that's something I should definitely look at because with ocean acidification, there's more carbon in the system, so that'd be really interesting to look at.
Any other questions?